presenting a paper titled Think Smart, Play Dumb, a game-theoretic approach to study deception in hardware Trojan testing. So, welcome Tapadhir to Cyber Science. I look forward to your presentation. You have approximately 20 minutes for presentation so that we leave enough time for questions at the end. Over to you.
All right, well, thank you so much everybody for coming to my talk. Just to reiterate, my name is Tapadhir Das. I am a recent master's graduate from the University of Nevada, Reno, and then I'm an incoming PhD student in the Computer Science and Engineering Department under Dr. Shamik Sengupta. And today I'm going to be talking about my paper that is labeled Think Smart, Play Dumb, Analyzing Deception in Hardware Trojan Detection Using Game Theory. Now, cyber deception is actually this new and trending topic that is widely being researched in the field of cybersecurity, specifically from the game-theoretic side of things. What we've done in this paper is that we've basically taken the concept of cyber deception and tried to incorporate it into supply chain security. Now, cyber deception in a nutshell basically means that using any kind of misrepresentation or deceiving method to kind of ward off adversaries or defenders to kind of distinguish between fact and fiction, what is what. So in this paper, first and foremost, I will be talking, actually one sec, about, perfect. So first and foremost, I'm going to be going over the background on integrated circuit manufacturing, along with talking about having good, proper motivation for good testing resources. Then I'm going to be talking about the contributions of this proposed paper. Further, I'm going to introduce the system model or the game scenario, and then going to talk about the static game formulation. Then I'm going to introduce the prospect theory, which actually models human subjectivity and rationality, and then further going into a repeated game formulation. Then I'm going to be showcasing deception using hypergame theory, which is like the biggest topic that I'm proposing in this paper. Further, I'm going to be going into our simulation and results, and then finishing off with a conclusion and future research potential of this paper. Now, as you look around yourselves nowadays, you see a ton of growth in technology. Things like IoT, AI, big data, autonomous vehicles, they've taken over cyberspace. And a lot of these technologies require a lot of processing power. So with the rise of these technologies, correspondingly, the manufacturing of integrated circuits or ICs have also increased. And a lot of IC designing companies, in order to reduce the costs, they've started offshoring the manufacturing portion of these ICs to third-party manufacturers, which leads to a potential for having supply chain security risk. And if you have a malicious manufacturing company, the one who has an incentive for attacking a certain IC designing company, they may try to corrupt the produced ICs with hardware Trojans. Now, what is a hardware Trojan? Well, a hardware Trojan is basically a malicious modification to the existing circuitry of an IC. And the whole point of it is to corrupt the functionality. You may have ICs that have hardware Trojans with multiple kinds of effects. Certain hardware Trojans can, say, slow down your phone's processor, or slow down your computer. Certain hardware Trojans can, say, leak information over covert channels. There are other hardware Trojans, even horrible ones, that actually have the ability to create backdoors into your system that attackers or hackers can later exploit. And the whole thing, and the biggest challenge with hardware Trojans, is that they're designed to be stealthy, meaning that they're not easily detected and don't get activated unless certain current, temperature, voltage, certain operational parameters get met. So when the produced ICs are brought back to the designing company, it is imperative that the designing company tests adequately for the ICs. Now, the most common ways to test ICs in today's day and age is it's between destructive and non-destructive methods. They include methods such as logic testing or side channel analysis over here. And the issue is that with large sizes of ICs in today's standard, it is very infeasible for these current methods to test for every potential Trojan type on a given IC. However, a promising approach that has been studied in literature recently is to use game theory. Now, using game theory, we study the interaction between the players in the scenario. The players being an attacker, whose job, and we try to find out what their probability over a certain number of Trojans is, and the defender find out their probability distribution over acting strategies. So what do we propose in this paper? Well, in this paper, we're proposing a multi-level game theoretic framework that are based on player rationalities and includes the concept of deception. Now, I'm going to be going a lot more into that in the further slides. So here's our system model. In our system model, we have an attacker, who is the malicious manufacturing company. You have your defender, who is the test engineer for the designing company. The attacker can insert one Trojan T, which is an element of tau. Now, tau is a set of all Trojans that can be embedded on a given IC. Each Trojan T provides a reward of V of T. Now, the magnitude of V of T kind of reflects upon the type of damage that this particular Trojan can do, and in turn provides a monetary reward to the attacker if undetected. Now, another important assumption, that is an assumption that has been made by a certain number of previous papers, is that every single IC is actually separated into various partitions. The reasoning behind it is that every single Trojan requires different operational parameters. Some Trojans may need more current, some may need access to a different voltage, some may need different temperatures, some may need access to the clock, an AND gate, an OR gate. Due to having various different operational parameters, every IC is separated into various partitions where a unique Trojan is placed on said partition. For the defender side, due to having limited testing resources, the defender can only test for a subset of Trojans, not all the Trojans. Now, if a Trojan is detected by the defender, the attacker incurs the attacker's fine, basically meaning that for playing that certain Trojan, they incur a fine. And the magnitude of this attacker fine can be very, very, very vast. Like you could have, if it's like a low-risk Trojan that was caught, then it could be a monetary fine. If it's like a very, very high-risk Trojan that was caught, it couldn't even lead to like termination of contract between the manufacturing company and the designing company. So we take a look at the static game. So in the static game, we have two players, attacker and the defender, in a set, which is number of players, which is both the attacker and the defender. S is the vector containing the strategy spaces of both the attacker and the defender. U is the utility functions for both the attacker and the defender. Now, the strategy space of the attacker is equal to tau. So the attacker strategies is basically the types of Trojans that they can play, where every single strategy in the strategy space is equal to every Trojan in tau. Now, K is basically the number of Trojans that the defender can test for per IC. Now, so the value of K is contingent upon the availability of resources for the defender. Now, the size of the defender strategy space is going to be tau choose K. This will be a little more evident as we go into the simulation results. For the utility of the attacker per IC, it takes in both the attacker strategy and the defender strategy for that particular IC. And the attacker's utility is going to be the attacker's fine if the strategy chosen by the attacker is an element of the strategy chosen by the defender, meaning that they got detected. If they're not detected, they get a reward, which is the attacker's reward for not being detected. Now, for the utility of the defender, we had to kind of minimize it a little bit because the whole point of it is the fact that we're trying to get an idea of how this would affect in a game theoretic scenario. In the real world, when you try to terminate contracts, you try to terminate a contract and find a new manufacturing company, it will take a ton of time. So in order to minimize and simplify the scenario, we just basically give it monetary rewards in this particular scenario, where a higher value monetary fine means a much more severe consequence was levied on the attacker. And in this, also in a couple of papers and also in this paper, what we've assumed is that both utilities are exactly the opposite, meaning that if detection happened, the reward that the defender gets is equal to the monetary reward that the attacker loses in the fine. On the other hand, if there is no detection on a particular IC, the reward that the attacker gets is going to be equal to the monetary amount that the defender loses due to not being able to detect, basically turning this game into a zero-sum game. So therefore, the utility of the defender is going to be negative of whatever the attacker's utility is. Now we come into prospect theory. Now, prospect theory is where we tend to get an idea or mathematically model how to mathematically model player subjectivity. Now, in general game theoretic terms, what happens is that we always tend to assume that players will be completely rational, meaning that they're always trying to optimize their expected utility at all times. However, in the real world, we know that that is not true. We face uncertainties, we face roadblocks, right? And we don't know all the information about a given scenario. So we might not play most rationally, even though we think we are. In the grand scheme of things, we are not. So under prospect theory, players tend to deviate from their most rational strategies when we face an uncertainty. So case in point here. So as both players are human in this game scenario, there could be many reasons for uncertainty. You could have issues with company regulations that prohibit certain strategies from being played. For the attacker, say if you don't have adequate resources to play Trojan type A, then the defender, if they know this, they'll place less weight on the attacker playing Trojan type A. consequently, on the other side, if the defender doesn't have adequate resources to test for Trojan type D, so if the attacker knows this, they'll place less weight on the defender playing for Trojan type D. So to capture this deviation, a weighting effect W is employed. A very important parameter here is the alpha parameter. The alpha denotes the rationality of a player, which ranges from 0 to 1. If you're 1, you are fully rational and always optimizing your expected utility. If you're 0, that means that you are completely irrational, and the fact that you give equal subjective weight to every event from happening, regardless of the probability that the event will actually occur. Now, in game theory, a very prominent equation that is used to kind of capture this weighting effect is basically the prelec, or the probability weighting function. And case in point, I can showcase you what I mean by that in the graph over here. So this graph showcases the objective probability of an event that is going to happen, and then the subjective evaluation that the event's going to happen based on player rationality, which every curve is basically signifying. So say like there's an inflection point over here, which is about at 0.37. And on either side, player rationalities tend to flip the order at which they kind of weigh certain strategies. So case in point, if let's say we have an event that has a low probability of happening, say, knock on wood, hope it doesn't happen, but tomorrow a big meteor is going to hit the Earth. Now, just objectively speaking, that say it has a low probability of happening. Say that has a probability of happening of 0.1. A much more irrational player, which is like, say, alpha of 0.2, will give it more subjective weight than that of 0.8, which is more rational. On the flip side, say if there's an event that has a high probability of happening. Say in the Northern Hemisphere, we're coming into summer, right? So I can safely say that it's going to be sunny tomorrow. And that's a pretty high probability bet that I'm willing to take. So let's say the event of that happening is, say, 0.9. Now, a much more irrational player will give it less weight that that event's going to happen than a much more rational player. And this is how we tend to compute subjectivity based on how rational a player is. And that affects the probability distribution of the players. So now we come into the repeated game scenario. Well, the repeated game scenario basically showcases multiple batches. So whenever the attacker, or no, so whenever the manufacturing company sends back the ICs to the designing company, it will be in multiple batches of multiple ICs. So there's a repeated interaction over every IC, or most of them ICs, between the two players. Now, I previously stated, checking all ICs for all types of Trojans is very much infeasible. So what do we propose in this paper? Well, we propose that the defender, in order to minimize their time and effort, will learn about the attacker strategies. So what happens is that you have all these batches. What will happen is that you will take a small subset of batches at the start and do an exhaustive search over all the learning, over all these batches, to kind of get an idea of what the attacker's probability distribution over their IC, over the Trojans are, and the corresponding rationality of the attacker. And once you learn that, you can transfer this learning to the rest of your batches in order to save time, be more efficient, and save money at the end of the day, right? So using this framework, the repeated game can be divided into two stages. You have the learning stage, and you have the actual game stage. Now, with it comes a couple more parameters. You have C of L, which is the number of tested ICs per batch in the learning, and you have C of A, which is the number of tested ICs per batch in the actual game. And we assume that the number of tested ICs in the actual game will be a lot less than that of the learning, because you're going to be testing for less ICs, because you've kind of get an idea of what the attacker's probability distribution is. So now we introduce the deception, and we introduce the deception using hypergame theory. So first and foremost, let me go into kind of an idea of what deception is. Well, deception, in just like in everyday senses, sometimes we tend to misrepresent ourselves in order to get higher utilities later on. Sometimes we have a tendency of making people think that we are somebody we're not in order for us to be in a more advantageous position. It depends on the context, but yes. And we're trying to capture that in this game theoretic scenario. And actually in game theory and cyber deception in general, this is what we're trying to capture. So we're trying, like, case in point being, say, if you're playing poker. So if you're playing poker, you may try to, if you're playing against a new opponent, you may try to think about, hey, does this person have any sort of tendencies, right? Do they have tendencies of bluffing? Do they have tendencies of betting big, going all in if they have certain tells, right? You try to learn these things about your opponent by misrepresenting yourself. At the same time, you learn about them so that you can use this learning to your advantage in the end game when the stakes are higher. Case can be made for like chess or any kind of strategic interaction. So in order to capture this, we use hypergame theory. Now, hypergame theory is an additional expansion on traditional game theory. Basically, there are additional levels of gameplays and utilities available on top of a base level, which are only available to a subset of players, which creates an unbalanced game where all players don't necessarily have the same view of the game. Now, what do I mean by view of the game? Now, say, I'll give you this a very easy example here. Say I'm player 1, and I'm playing a static game with player 2, and I'm playing static game A. I know player 2's focus is stat game A. Player 2 is assuming my focus is also this game A. But player 2 doesn't know that I'm also playing another static game with player 3, and I'm playing game B over here. Now, the same scenario happens over here. One, I know that their focus is game B, but they assume my focus is game B. Now, the thing is, my strategies that I select in game A affect my utilities in game B. So therefore, I will not be playing either game with complete rationality. Player 2 and player 3's view of the game is going to be their static games, while my view of the game is going to be both game A and game B. And that is kind of how we kind of promote this hypergame theoretic application. So in this game, what do we propose? Well, we propose that the attacker will be playing dumb. We are assuming that the attacker knows that they're being learned about. So if they're a cunning attacker, they may try to act dumb. Now, acting dumb means during the learning stage, they will have a much more low rationality behavior. In the game stage, they will actually flip to their actual high rationality behavior. The point being is that during the learning stage, if they do the low rationality behavior, the defender will learn about this and assume this behavior will happen in the game stage. In the game stage, the attacker's actual rationality will showcase over here. Now, deception rationality is going to be what we call the irrational behavior, and the actual rationality is what we call the actual behavior. And we assume that the deception rationality is a lot less than that of the attacker's actual rationality. So case in point over here, if you take a look at this graph, this figure over here, you have both the defender and the attacker's viewpoints. The defender is assuming that some game is happening. However, the attacker has a much more higher viewpoint of the game because they've deceived successfully the defender. So now we come into our simulation parameters and the static game scenario. First, we have tau, which is again the set of all Trojans that the attacker can use on a given game. So tau is A, B, C, and D, which is the 4 types of Trojans. You have the strategy space of the attacker, which is going to be tau. You have K, which in our case is 2, and K can change based on the availability of resources for the defender. Strategy space of the defender, if you remember previously, it was tau choose K. It was 4 choose 2. That means it's 6. And basically, it's a combination of K of all the certain Trojans that they can test for per IC. V is the reward vector, F is the find vector, PA and PD are both the initial probability, objective probability distributions of both the attacker and the defender over their strategies. The rationality of the defender is 0.5, the rationality of the attacker is 0.5 as well, and the rationality of the deception rationality of the attacker is 0.1. Now, this was computed using equation 14 from the paper. I was not able to put equation 14 on this particular presentation due to time and space constraints. Now, C of L is the number of tested ICs per batch in the learning, and C of A is the number of tested ICs per batch in the game. And this table basically showcases the static game, where you have both the attacker, the defender, their corresponding strategies, and their respective utilities based on said strategies. Now we come into the simulation and results section. So on the left-hand side, we have a graph that showcases the attacker's actual rationality, and then correspondingly, the attacker's utility gain with deception. And this is based on the fact that they're using a 0.1 rationality for their deception. And so the actual rationality tends between different kinds of attackers with different rationality types, and every single graph showcases them facing a certain type of defender. And what do we find here? Well, we find that irrespective of the actual rationality of the attacker, the utility gain will be maximum when facing a defender with equal or lower rationality than they are. Case in point, if you're an attacker with an actual rationality of say 0.5, your utility gain will be the most when you face a defender say of 0.5 as well. If you have an attacker whose rationality is 0.6, the utility gain will be maximum when you're facing a defender who is 0.5 or 0.6. On the other hand, if a defender's rationality is say greater than 0.6, so these 3 lines over here, the attacker's will achieve a positive utility gain. But the order becomes a lot less predictable because case in point, if you're an attacker who's say a 0.5 rationality, you will gain a higher utility if you're facing a defender who's 0.9 than that of 0.6. And if you're an attacker who has, say, a 0.6 and a 0.7 rationality, you will get a much higher reward playing facing a defender who is 0.9 than that of 0.8. Also, another important observation that was made is that an attacker with higher actual rationality, so over here, does not mean that they necessarily make more utility gain against their lower rationality counterparts when facing the same defender. What do I mean by that? Well, say if you have a defender who is, say, 0.7 rationality, the best utility gain against that defender will be one who has a 0.6 rationality. And if you, say, have a defender who is, say, a 0.6 rationality, the best utility gain will be for an attacker who has a rationality of complete rationality, or 1.0. What does this tell us? Well, it tells us and it corroborates the importance of the hypergame theory, which has all these different rationalities. And it showcases that as a maximum achievable unit, it varies deeply based on what kind of rationalities players are using. And the optimal deception is always going to be the one that you compute using equation 14. For us, it was 0.1. For another scenario, it could be 0.3, it could be 0.4, like it based on what you compute with. Now, on the second figure, we have the attacker's deception rationality on the x-axis, and you have the attacker's dummy rationality or deception, attacker's utility gain with their deception rationality. Again, it's 0.1 in this case. And what with every single graph showcases the attacker's rationality utility gain based on if they go from their deception rationality to their actual rationality. So we find that using a deception rationality of 0.1, it provides the highest utility gain for any attacker whose actual rationality is, say, greater than 0.3, as you can see over here. Now, if an attacker has an actual rationality of, say, 0.3 or less, you see that they don't really gain a lot of utility by deception. But an attacker with an actual rationality of greater than 0.3 has massive utility gain with deception if they choose to deceive below a 0.3. Well, what does this show us? Well, it corroborates the finding of the pre-like or probability weighting function that we showcased, where we have a flipping order at, say, 0.37 over here. And order on either side, attackers of various degrees of rationalities tend to flip their orders upon which they provide subjective weights on the the objective probability of an event happening. In this game-theoretic scenario, we use a deception rationality of 0.1 because that is what was computed. But it is not a general case. Optimal deception rationality has to be computed for each case scenario using equation 14. So in conclusion, in this paper, we showcase a framework for hardware testing. Prospect theory is used to model the utilities for players with various rationalities. We showcase a repeated game scenario where the defender tries to save on time and resources by learning about the attacker's tendencies. We implemented an attacker deception that is based on the pre-like function premise and models the scenario using hypergame theory. We simulated the results and it shows us that the attacker can successfully deceive the defender and insert Trojans without being detected. So in future work, we plan on building more rigorous deception mitigation techniques for the defender using concepts such as moving target defense and additional levels of hypergame theory. That has been all in my presentation. Thank you so much for joining again. Does anybody have any questions?
Thanks, Tapadhir. It was a very interesting presentation. We have a few questions already. So let's go straight into them. So the first question says, let me find it, okay. So COMP uses hypergaming to explain how information warfare ties into the four canonical strategies of denial, deception, mimicry, disruption and destruction, and subversion. Have you explored COP's four canonical offensive information warfare strategies in your research?
For this particular research, we did not do it, although that is actually a very good future research topic that I can take a look at.
Okay. Then another question is, where do you think this could be placed in the manufacturing pipeline?
So in the manufacturing pipeline, it's important because the thing with hardware Trojans is the fact that, again, it's really hard to detect. So based on this case in point scenario, you may need to kind of get an idea of, in the manufacturing pipeline, I would say that you may try to Is it okay if I take a second to think about this?
Yeah, absolutely. Do you want to move to the next question?
Sure, yeah.
Yeah.
That's a very good question, actually. Thank you.
So how did you achieve equilibrium in the game theory, especially with hypergame?
So it wasn't, I couldn't actually show it in the presentation because of the time and space constraints, but we do have a proposition in our actual paper that showcases a hypergame Nash equilibrium, and we also have a proof that goes along with it.
Okay.
So it is available in the paper.
Super. And what advantages do you think hypergame provides over normal game theory?
So the concept of hypergame theory is that it makes a unbalanced playing platform. And whenever you have an unbalanced playing platform, certain subset of players may have an advantage over the other subset because they have access to more information and they have more kind of access to different levels of utilities. So using a hypergame theory scenario, it means that one player will be more advantageous to a position, therefore it creates a misbalance.
Okay, super. Do you want to go back to the previous question? Answer?
Sure.
Feel free to take a few seconds to think about that if you need it.
Yeah, thank you. So the way this could work is that it comes back into, so the attacker will try to employ the deception protocol, but for the defender, you may have to kind of come up with techniques in order, because you can assume that, again, you don't really know what's happening, right? But because deception can be a point of case in this, when you're doing testing, you may have to kind of employ additional approaches to kind of thwart this deception. This approaches can be like something like, maybe when you're doing learning, right? When you're doing the learning stage, you don't do the full learning stage completely. You may break it off into middle of the game and then the end of the game, so that you may try to save on resources, and you can try to, because it's basically trying to come up with applications where the defender will kind of get an idea that they're being deceived. And it's kind of a hard question to answer because, like, you have to, there are multiple, and it's a pretty open-ended question. So there are like multiple ways that this can be implemented, and I don't exactly know which one would be the most effective.